In this part of hydrogen and hydrogen-like systems, I shall be going to discuss the solution of the radial part of hydrogen or hydrogen-like atoms. The separation of variable method leads to the following expression for the radial part of the Schrodinger equation of hydrogen atom or hydrogen-like systems, that is 1 by psi r d by dr r square d by dr psi r minus 2m r square divided by h cross square into Vr minus E, that is equal to L into L plus 1. This equation is solely connected with the radial aspect of electron's motion, that is its motion towards or away from the nucleus. However, we notice that the presence of E, the total electron energy in this equation. The total energy E include electronic kinetic energy of the orbital motion, which should have nothing to do with its radial motion. This radial equation, by using the concept of reduced mass and the Coulombic potential as Vr, that is equal to minus E square by R in atomic unit, by substituting this reduced mass and Coulomb potential, we can write the radial part of this Schrodinger equation as 1 by psi r into d by dr into r square d by dr psi r minus 2 mu r square divided by h cross square into minus E square by R minus E, that is equal to L into L plus 1, or d by dr into r square d by dr psi r minus 2 mu r square divided by h cross square into minus E square by R minus E into psi r minus L into L plus 1 into psi r, that is equal to 0, or d by dr into r square d by dr psi r plus 2 mu r square divided by h cross square into E square by R plus 2 mu r square divided by h cross square into E minus L into L plus 1 into psi r, that is equal to 0. One approach to solve the radial equation as a power series solution, which involves two main steps. First, relate the radial equation to the associated Legure equation, for which the associated Legure functions are the solutions. Then find the Legure polynomials as the solution of the Legure equation. That is x into L double dash j into x plus 1 minus x L dash x plus j into Lj into x, that is equal to 0. Legure polynomials of any order can be calculated using the generating equation, that is Ljx, that is equal to e raised to x into dj divided by dxj into e raised to minus x into x raised to j. The Legure polynomials do not form an orthogonal set. The related set of Legure functions, that is phi jx, that is equal to e raised to minus x by 2 into Lj into x, and this equation is orthonormal in the interval, that is when the value of x is in between 0 to infinity. The Legure functions are not the solutions to the Legure equation, but are the solutions to the equation which is related. Just as Legure equation becomes the associated Legure equation by adding the appropriate term containing the second index, the associated Legure equation is x Lj k double dash into x plus 1 minus x plus k into Lj into k dash x plus j into Lj raised to k into x, that is equal to 0. And this equation reduces to Legure equation when the value of k is equal to 0. here in the case of hydrogen atom we are interested only in those Legure polynomials where the k value is less than j for this system. The associated Legure polynomials can be calculated from the Legure polynomials using the function Lj raised to k into x minus 1 raised to k into dk by dx raised to k into Lj plus kx, where the Legure polynomials are not the associated orthogonal but the Legure functions of the type that is phi j k x, that is equal to e raised to minus x by 2 e raised to k by 2 Lj k. These are orthogonal in the interval range in between x is in between 0 to infinity, and this can be made an orthogonal set. Again, the phi j k are not the solutions to the associated Legure equations but are the solutions of the related equations. We are specifically interested in a slightly different associated Legure functions than the usual first choice of the indicated in the above equation. That is, we are interested in this type of Legure equations, that is yj k x, that is equal to e raised to x by 2 into e raised to x raised to k plus 1 by 2 into Lj raised to k. These are also not the solutions of the associated Legure equations but are the solutions to the following equation, that is yj k double dash x plus minus 1 by 4 plus 2j plus k plus 1 by x minus k square minus 1 divided by 4x square into yj k x, that is equal to 0. That is, our interest is the equation 47 and its solution 46 is that the equation 47 is in the form of the radial equation. So radial solutions of psi r, that is we need the solutions as psi nl r, that is equal to a into y n raised to 1 r, where a is simply the normalization constant. So we are interested only the equations of the type 47 only. Then our next task is to express the equation 39 in the form of which is comparable to the associated Legure equation 47, and we have already know the solutions of equation 46. We will be made able to glean an additional information by comparing the equations term by term. The energy levels of the hydrogen atom and the meaning of the indices of the associated Legure polynomials, which will be the quantum numbers for hydrogen atom. Then we will make 3 substitutions to get the equations in the form of 47. That is, first one is put a substitution like that yr, that is equal to y is a r is a function of y, that is yr, that is equal to r psi r, that gives the psi r is equal to psi r, that is equal to yr divided by r. Making this equation in the first term and evaluating the derivatives, then we get d by dr into r square d by dr psi r, that is equal to d by dr into r square d by dr into r raised to minus 1 into yr, that is equal to d by dr into r square into minus r square yr plus r raised to minus 1 dyr by dr, that is equal to d by dr of, on simplification, this d by dr of minus yr plus r into dyr by dr, or dyr by dr plus minus dy by dr plus r d square yr by dr square, that is equal to r into d square yr by dr square. The substitution serves to eliminate the first derivative. So we could have both the first and second derivative if we had evaluated the first term using psi r. With this and the substitution in equation 47, then the equation 39 becomes r into d square yr by dr square plus 2 mu r e square divided by h cross square plus 2 mu r square h cross square into e minus l into l plus 1 into yr by r, that is equal to 0, or d square by yr by dr square plus 2 mu e square by r h plus 2 mu e by h cross square minus l into l plus 1 divided by r square into yr, that is equal to 0. Then we make the second substitution, and it is essentially simply we are giving another notation, that is epsilon divided by 2 the whole square, that is equal to minus 2 mu e by h cross square. That is, instead of minus 2 mu e divided by h cross square, we are putting a substitution epsilon by 2 the whole square, where the negative sign on the right hand side indicates we are looking for the bound state in which energy is less than 0. So including the negative sign here, let's have the epsilon which is real. The last equation becomes, then the final equation, the above equation becomes, by giving this substitution in terms of epsilon, we get d square by dr square into yr plus 2 mu e square by r into h cross square minus epsilon square divided by 4 minus l into l plus 1 divided by r square into y into r, that is equal to 0. Then we make the third substitution, that is, it involves the change of variables, and notice that it relates the radial distance and the energy through the equation 49. That is, we can relate the epsilon in terms of x and r. That is the x, that is, we substitute x as r into epsilon, or r is equal to x by epsilon. This is the third substitution. Then we find dr. dr is equal to dx by epsilon. Then take the second derivatives, dy r by dr square, that is equal to d by dr of d by r by dr, or epsilon into d by dx into epsilon into dy x by dx, or this becomes epsilon square into d square by dx square into yx. That is, here we are expressing the dr in terms of epsilon. So by making the three types of substitutions, this radial equation becomes epsilon square into d square yx by dx square plus 2 mu e square into epsilon divided by x into h cross square minus epsilon square by 4 minus epsilon square into l plus 1 by x square into yx, that is equal to 0, or d square yx by dx square plus minus 1 by 4 plus 2 mu e square by epsilon x h cross square minus l into l plus 1 divided by x square into yx, that is equal to 0. And the equation 51 is exactly the equation 47, where the value of l into l plus 1, that is equal to k square minus 1 by 4, or from this k square minus 1 by 4, that is equal to l into l plus 1. From this we can find out the value of k, that is equal to 2l plus 1, and the 2 mu e square by h cross square into e, that is equal to 2j plus k plus 1 by 2, and it is given as equation 54. As mentioned earlier, we got the solutions of the equation 47 just after the above two substitutions. That is, by substituting the equation 52 and 54 in equation 46, we get the equation 46. That is, by making the above substitution, we get the solution as the solution of the radial part of the Schrodinger equation as y j k into x, that is equal to e raised to minus x by 2 into x raised to k plus 1 by 2 into lj raised to x. Then next we have to find out the energies eigenenergy values of the radial part of the Schrodinger equation of hydrogen or hydrogen-like systems. The equation 53 tells us that K is equal to 2L plus 1, and the equation 53 gives the energy eigenvalues of the hydrogen atom, but it requires some development since we know that K is equal to 2L plus 1. Then by substituting the 2J plus 1 plus K by 2, that is equal to 2J plus 12 plus 1 plus 1 by 2, that is equal to J plus L plus 1. From the discussion on the associated Legure polynomials, the indices J and K are non-negative. The sum J plus L plus 1 can therefore assume any integer value of 1 which is greater. Therefore, we are going to rename the quantity J plus L plus 1 as equal to 1. That is n is equal to J plus L plus 1. The new integer, the new index n, is known as the principal quantum number. Using the principal quantum number, the following energy eigenvalue expression can be derived. That is, from the equation 54, that is 2 mu e square by h cross square into E, that is equal to 2j plus k plus 1 by 2. The equation 50, and from the equations 55 and 56, we can write J plus L plus 1, that is equal to n, that is equal to 2 mu e square by h cross square into E, or epsilon, that is equal to 2 mu e square by h cross square into n, or epsilon square, that is equal to 4 mu square e raised to 4 divided by h cross square into n square. Then substituting the equation 49, that is epsilon square by 2, to the eliminate the epsilon and insert the value of energy. This gives minus 4 into 2 mu e divided by h cross square, that is equal to 4 mu square e raised to 4 divided by h cross square into n square, or E, that is equal to mu square e raised to 4 h cross square divided by 2 mu h cross raised to 4 into n square. And from this equation, we can find out the value of energy eigenvalue En, that is equal to minus of h cross square divided by 2 mu a0 square n square, since we know that a0 is equal to h cross square divided by mu e square, or En, that is equal to minus h cross square divided by 2 mu a0 square into n square. Here a0 is equal to minus h cross square by mu e square. By substituting the constant values, we get the Bohr radius as 0.529 angstrom. Then by inserting the numerical values of the constant in the equation En, we can find the value of En as equal to minus 13.6 electron volt divided by n square, where the quantity 13.6 electron volt is called a Rydberg constant, and which is usually denoted as R or Ry. The ground state energy is E0, that is equal to minus 13.6 electron volt when n is equal to 1. It is often convenient to express the excited state in terms of the ground state energy. Then the radial part of the wave function becomes, that is the solution of the radial part of the wave function becomes yjkx, that is equal to e raised to minus x by 2 into x raised to k plus 1 by 2 into L j k raised to x, since we know that the k is equal to 2L plus 1 or k plus 1 by 2. So that is equal to 2L plus 1 plus 1 by 2, that is equal to L plus 1, and j plus L plus 1, that is equal to n, that gives j is equal to n minus L minus 1. Then by substituting the value of j and k plus 1 in the equation, we get yn raised to L x, that is equal to e raised to minus x by 2 into x raised to L plus 1 into L n minus L minus 1 raised to 2L plus 1. So the solution starts to assume some traits of the hydrogen atom. The independent variable is still x, that is equal to epsilon r. We need an independent variable r, or at least in terms of r, to be consistent with the spherical polar coordinate system. Using the equation 49 and 58, we can solve this equation in terms of epsilon, in terms of Bohr radius and the principal quantum number, or the epsilon by 2 the whole square, that is equal to minus 2 mu e divided by h cross square, that is equal to 2 mu by h cross square into h square by, or minus h cross square divided by 2 mu 0 into n square mu a0 square, that gives 1 by a0 square n square, or epsilon square, that is equal to 4 by a0 square n square, or epsilon is equal to 2 by a0 into n, or x is equal to 2r by n a0. And this is the term, this is in terms of the desired independent variable, that is r, y n raised to l r, that is equal to e raised to minus r by n a0 into 2r by n a0 raised to l plus 1 into l into n minus l minus 1 raised to 12 plus 1 into 2r by n a0. Finally, we can relate the associated Legure functions to the radial functions in order to find out the solution for the equation 48. That is, or we remember that yr is equal to r into psi r. By inserting these values, the radial part of the wave function, the solution of the radial part of the wave function becomes r into psi nlr, that is equal to e raised to minus r by na0 into 2r by na0 raised to l plus 1 into l n minus l minus 1 2l plus 1 into 2r by na0, or psi nlr, that is equal to a into e raised to minus r by na0 into 2r by na0 into l into n minus l minus 1 raised to 2l plus 1 into 2r by na0, where here we added the normalization constant, which has the value that is equal to 2 by na0 from the power term when we cancel the factor of r. This still needs to be normalized. We want the radial functions to be individually normalized so that the product of the radial wave functions and the spherical harmonics of the hydrogen wave functions is already normalized. Therefore, the normalized radial wave functions of hydrogen atom becomes psi nlr, that is equal to, that is here the derivation is not required, and the normal value of normalization constant, that is equal to square root of 2 by na0 raised to 3 into n minus l minus 1 factorial divided by 2l into n plus 1 factorial whole raised to 3 into e raised to minus r by na0 into 2r by na0 raised to l into n minus l minus 1 raised to 12 plus 1 into 2r by na0. And by substituting the values of the variable functions, we get the first few radial wave functions of hydrogen atom. They are psi 10r, that is equal to 2a0 into e raised to minus 3 by 2 into e raised to minus r by a0, or psi 20r, that is equal to 1 by root 2 into a0 raised to minus 3 by 2 into 1 minus r by 2a0 into e raised to minus r by 2a0. Then psi 21r, that is equal to 1 by root of 24 into a0 into raised to minus 3 by 2 into r by a0 e raised to minus r by a0. Psi 30, that is equal to 2 by root 27 into a0 into minus 3 by 2 into 1 minus 2r by 3a0 plus 2r square by 27a0 square into e raised to minus r by 3a0. Similarly, psi 31 and psi 32. References: Quantum Chemistry, R.K. Prasad. Second one, Concept of Modern Physics, the 6th edition, author Bezier, McGrew-Hill Higher Education, and this chapter 10 of the hydrogen atom. It is from the website http://faculty.washington.edu. It is a Google PDF.